PCS members and friends to our PCS IBS seminar. Today we have a pleasure of hosting Dr. Upendra Kumar from Korean Institute of Ceramic Engineering and Technology. And our scientific host today is Sergey. Sergey, please.
Yeah, welcome everyone. So it's a pleasure to have Dr. Upendra Kumar with us. Let me give you a few. Where do I have to stand actually so that the cameras work? We have to stand here, right?
Yes.
Okay. So right to you, right to the speaker. So let's see, what did he write here in his CV? So he did his bachelor at in Kanpur at the CSJM University in Kanpur in India, and he also finished his Master of Science there in 27, and then he moved to the IIT, Indian Institute of Technology in Guwahati, where he did his PhD and finished the PhD in 2018. Then he moved to Vilnius University in Lithuania, where he had a postdoc or visiting research fellow stay. And then he moved to some very interesting place, which is called Indo-Korea Science and Technology Center in Bengaluru. And I checked this thing really exists. I never heard about this, where he spent 3 years as a postdoc. And then from there, he moved to another IIT.
No, the IZ, Indian Institute of Science.
Oh, sorry. Indian Institute of Science, Education and Research. That's the ER in Pune, where he stayed not for a long time, half a year. And then he moved to the Korea Institute of Ceramic Engineering and Technology, where he is a staff scientist since 2021. And today he will talk about Floquet engineering, which is probably not very much related to ceramics, but
yes,
very much related to maybe some of our interests. So let's welcome the speaker. The floor is yours.
I want to thank you, Professor Sergey, for giving me this opportunity. So actually, I have done this work during my PhD. After 2018, I involved in machine learning and computational physics. So this is some kind of my PhD presentation, what I have done during my PhD. So Floquet engineering, and it is well described there. So what I have, this is outline of my presentation, that classical Floquet oscillation, then Bloch-Siegert shifting Floquet oscillation, and then we have developed some method for conventional Floquet oscillation, which is defined there. So we developed some Fourier transform method. Then for detecting Floquet oscillation, I used Floquet pump roller spectra. Then what is quantum nature of Floquet oscillation, and then some. So what is Floquet oscillation? So application of high frequency electromagnetic field allow for control over electronic parameters of condensed matter structure, and such controlling known as Floquet engineering, which is based on the Floquet theory for periodically driven condensation. So what happened that a periodic exchange of energy between light field and two-level system is known as Rabi oscillation, and frequency is determined by external applied field. So actually this Rabi frequency is defined like this: omega is equal to P dot E by H bar, where P is dipole moment, is external applied field. So here I am trying to show some kind of exciton behavior. So next, so what actually I want to say. So if this is there is electron from valence band to conduction band, so there is 3 possibilities that if we apply external field, then there will be suppose if external field is less than this band gap, then there will be no oscillation, and if external field is nearly equal to this band gap, then there will be Rabi oscillation, and if external applied field is far than this band gap, then there will be Floquet oscillation. So in some sense, I can say that the Floquet oscillation can be said close cousin of conventional Rabi oscillation of resonance case. So what I want to show here, that suppose I have taken this example of graphene. So in graphene, this is a traditional picture that lattice A and lattice B. So what we do that we do some creation and enumeration of operators. So just to be put light here, and then there will be electron is annihilated on A side and it moves from B to A, so creation and annihilation type of things. So what happened in Floquet oscillation, we take Hamiltonian of Dirac while fermionic system at low energy. It comes via tight binding approximation. So this type of Hamiltonian comes here, and then we apply electromagnetic field. So sigma dot p type of things, and here just we applied external electromagnetic field. So and this is that Hamiltonian written in second quantized form. So there Greek indices like sigma up or spin up or spin down, and C dagger, C creation only has been operated, and we have applied this external vector potential. So what we do that we just in a traditional Floquet theory, they just write this expression Hamiltonian, they break in this form and wave function in this form, and then considering that assumption that regard external driving frequency is much larger compared to band gap. So what happened that we substitute this expression in equation, Schrodinger equation, and Xi is equal to Esi, and drop higher order harmonics, and we get this type of Hamiltonian. So basically what we are doing from time dependent Schrodinger equation to time independent Schrodinger equation we change. And then the eigenvalue of this Hamiltonian known as Floquet frequency. So till here, it is well known and well established theory. So what I have done during my PhD, I start from there. So
can I ask a question?
Yes.
So you mentioned two, it's very general. So you mentioned two energy scales. That's the from the external electromagnetic field, and then one in the system. So how do you take account of scattering mechanisms in Floquet theory, or what about energy scales that which scattering mechanisms?
Can I finish then?
Yeah.
Okay. So then what I have done that during the external applied field. So there is, when we are applying external field, there are three possibilities that continuous external applied field. First we take, then we take first external applied field, and third case we take quantized applied field. So what I have done that then conventional Rabi oscillation are using by rotating wave approximation. So in this approximation, where rapidly oscillating term of effective Hamiltonian are removed. So then what happened that in rotating wave approximation, when counter rotating terms are taken into consideration, so there will be shift in resonance conditions came, and this is known as Bloch-Siegert shift. So what happened that when we take off resonance term, then there is a shift in resonance condition came. It's called Bloch-Siegert shift. So what we have done that study of Floquet oscillation in various different atomic system by considering external field as classical nature. So in resonance case, it has already known Bloch-Siegert shift. So I want to study Bloch-Siegert shift in perspective of Floquet oscillation and conventional Rabi oscillation. And for case study, I have considered wire semi-metal as an example. So what happened that what is already known in conventional Rabi oscillation, I try to mimic similar phenomena in Floquet oscillation because it is in off resonance case. So same thing, I have told you that I take low energy Hamiltonian and tight binding model. I applied external applied field, and then I use real vector potential, and I take case of circular polarization. So what happened that?
Yes, the question.
Yes.
You say you take into account low energy Hamiltonian, so the valence band and the conduction band. But if you apply high frequency electromagnetic field, don't you need to consider also higher energy bands in electronic structure?
Actually,
Because you have a very high frequency of period. Why the low energy theory here is applicable?
I don't get your question. Repeat again.
Oh, okay, you have valence band, you have conduction band, but next in the energy, up in the energy, you have also other bands, which are usually free of electrons. But if you apply very, high frequency electromagnetic field, you can excite that state.
But actually, because we are in such system, we are talking near about Dirac point. So we can apply external field near Dirac point in low energy physics. We are not going away from Dirac point.
But the frequency of an external field is very high.
Not very high.
It's not very high.
Not very high.
So,
It depends on the chemical potential that it put. If you just want to make the particle whole excitation, if the chemical potential is equal to 0, then this frequency equal to 0. So it depends on the chemical that it
in
put.
that sense,
Yes.
So what happened that I make a Bloch equation from these low energy Hamiltonian. So this is here NDIF and P are the polarization and population excess respectively. So I drive these Bloch equation after applying external field, and then I got. Then what I have done for solving these Bloch equation, I use Fourier transform method. So I convert them this time domain to frequency domain, and then apply same type. They are removing higher order harmonics. So I just remove them higher order harmonics, and then I take these momentum vector in spherical coordinate, and then I use both conditions for conventional Rabi oscillation for Floquet oscillation. So for conventional Rabi oscillation, I use this condition. So here is for resonance condition. I applied some mathematical trick, and then I found that frequency of conventional Rabi oscillation with help of this Fourier transform method, and same I applied with for Floquet oscillation, and with this condition I found with resonance condition. So here this is a Bloch-Siegert shift I found in perspective of Floquet oscillation. So this term here. So this term came here. It is some kind of change of resonance condition in Floquet in perspective of Floquet oscillation. So we found that okay, this is some kind of Floquet Bloch-Siegert shift in wire semi-metal which has inotropic nature. Same I found for conventional Rabi oscillation, and I found this is a Bloch-Siegert shift which is well defined here for graphene and for wire semi-metal, and which depend on the wave vector index. So here I try to show that okay how it's changed with wave vector angle. So here you can see that in Floquet oscillation it exists, and when we change wave vector angle to pi/2 it vanishes. So moral of the story, I want to say that there are some kind of Bloch-Siegert shift in perspective of Floquet oscillation. So next, as usual, I tried that okay how my calculation is correct. I applied a numerical simulation technique by using Mathematica, and I found that both the formula which I found by this Fourier transform method and the ND-solve routine in Mathematica, and I found that they are agree with each other. So till here, I use as a continuous external applied field. Now, my next goal was that if external field behavior changed, and it will be pulsed external applied field. So it means that for the reason that my goal was that how can we detect Floquet oscillation? So I studied Floquet pump probe spectra. So what happened that a theoretical study of pump probe experiment has been performed for detecting Floquet oscillation. So what we do in pump probe spectra, that we suppose this is a system. So first we utilize a pump for exciting this system, and then slow intensity same beam for probing that what happened that system. So this is kind of pump probe experiment which is well stabilized theory. So what I have done that I draw all the equation. It is very tedious mathematical model. So first I draw a pump equation that what happen when time is less than 0, though in this case system is in non-equilibrium, it means ground state and no external applied field. So the evolution equation has this form. Then I got this equation for t less than 0. Then I try second case when I applied external field from when pump field has applied, so time limit is 0 to TPU. It means when pump field applied, it means this external field has came into picture. Then I got a second equation after applying pump. Then third case, that what happened when we consider after pump has come to finished. So then after pump has finished, there some dephasing has came, and we put this type of dephasing there, and then applied some kind of dephasing here. So I got another equation after when after pump has applied. Now second time I applied probe equation, and then then I have again utilized same this evolution equation, and then there will, because pump and probe cannot be two simultaneous, so this belong from pump and this belong from probe is delta in difference between that. So I take only probe equation, then probe equation in this time when pump field has applied, then I check probe without pump, I got some equation, and then probe with pump, I got next equation. So finally, moral of the story, I want to got this differential transmission coefficient, which is defined as integrated probe strength with pump, integrated probe strength without pump, divided by integrated probe strength without pump. So because we are taking low energy Hamiltonian, so we are considering that physics which is very close to Dirac and Weil node. So therefore, it is imperative to look for physical quantity that are insensitive to short distance physics and are independent large momentum cutoff. So what I have done, I make this ratio because after doing this differentiation with the pump timing, expression become very clear because there are many very large expressions. So I just differentiate with respect to pump time and then divided by pump time. So here it is a TPU's pump duration, T0 is something.
Sorry, what is the physical meaning of this calculation?
It is some kind of differential transmission coefficient. And because I use this, because when I get differential transmission coefficient, it was many, in that formula, there was many TPU. So just I differentiated with some pump duration. So it become more simpler. It is just differential transmission coefficient. It is nothing else. Just divide two differential transmission coefficient at TPU and one other some fixed time. It is nothing, just differential transmission coefficient. What we do.
Yeah, but what is transmitted?
I'm talking about this.
Yes, what is transmitted?
Because when we give pump in some system, it goes. Then what happens inside system, we detect by probe. So here it means integrated probe strength with pump, integrated probe strength.
I'm asking you, transmission means that you transmit something. What? So you
External field. We applied external field of system.
And then something is transmitted. What? You measure current or something like this. What is transmitted? What are we talking? Electrons, phonons,
Photons, because
photons.
yes.
Okay. Transmitted through what?
Transmitted through like graphene, Weissman metal, and
Does it depend which direction you try to shoot it through, like this, in plane or perpendicular, or what are we?
Yes, I take circular polarization.
That's the polarization of the light. But
Yes.
How do you orient the light relative to the graphene probe?
Like
Perpendicular or parallel, or how do I have to do that?
means circular polarization. I take gamma is equal to pi by 2. Means perpendicular.
Perpendicular means through the plane of the graphene.
Yes. So then I got the expression, and from here I found some damping law for different, like for graphene, I found this type of question where damping law is 1 by 2, and for Weissman metal it is 5 by 2, and the same I tried for topological insulator. So in topological trivial case, it's like TPU, and a non-trivial case, it is like TPU square. So just I plot that, okay, I found that from this experiment, pump probe experiment, we can differentiate between graphene, topological insulator, trivial and non-trivial state, and vice versa.
How can you differentiate?
Because it has different damping law. Like
No, by looking at the figures.
figures just plot here.
Yeah,
You
so how
see?
can you differentiate?
Because it is very slowly damping and graphene is not very fast damping.
But compared to what? Slow and fast compared to what? What's the scale you compare to? Because if I see just one curve, how can I tell it's fast or slow? I can compare this.
Because for graphene, I think means there that time I want to compare between YSMA metal and this graphene. So I got just this expression. So if I want to compare two things, then I can compare. Otherwise, a single, what can I say? Because it is just expression.
A question. You bisect metal means that you have a three-dimensional giraffe
Yes,
and giraffe and
Y load.
Y load and two Y load, right? In the padding
Yes,
energy is across the Y load, two Y load.
yes.
This is but
In graphene, there is only one.
something is two-dimensional.
Yes, yes. But actually, for that case, we does not consider in z direction any potential. We just consider two dimension vector potential.
The semi-metal is there are bisect metal is many possibly.
Many possibilities.
You
But,
only
but I'm talking about only one Dirac node. I'm
one
doing
giraffe top pair only one.
one. Like similar to graphene, what happened in z direction and
You cannot have one Dirac node.
Two already pair, right?
while
But you
node.
have pair.
Yes, while node, two while node pair.
Two Y load.
Could you please show a figure from the previous slide? Just try to understand. So when you consider well semi-metal here, you have some enormous chi. So it's basically close to one at the first moments of time. So it's a system which is very out of equilibrium or something like that with your pump.
Actually, what happened that because when we detect with probe, it is after coming means excite, and when it comes normal form, then we use probe. There is some delay between pump and probe. Out of equilibrium, we can say excite because.
But I just trying to understand. Well, so chi is when chi is close to one, it means that your pump is very strong, not you get something concrete. Okay.
Then this time, first I applied continuous external field. Then first now I consider that if external field is a quantized form, means like a photoelectric effect. So what I why is it not coming properly?
What kind of pump laser do you have to you have pump and both. How to be get some laser light.
Actually, what happened that with what happened, I just because same in experiment same light is utilized for pump and probe. So in theoretical modeling, I just think that okay, some less intensity than pump. So just here, if you talk here, I just small this modification. This is a for vector potential for pump, and this is a small modification. A plus delta AP is for probe.
In order to have moving to see Floquet, you have to use parallax laser or what kind of laser?
Because I got expression, so from beginning, how I can say it comes in some reason. means alpha, infrared or ultraviolet, because I don't perform this experiment. I'm just theoretical modeling items. It is theoretical modeling.
You said in the experiment, I think it's a little bit important in the sense of the theory. In probe experiments, usually there is a very considerable difference in frequency between the front and the probe because you want to resolve something.
Yes.
Live.
Yes.
So, what is the you don't know the characteristic frequency from the front and the probe in the experiments?
Yes, actually, for the ultraviolet and infrared region, they have taken effect.
You assume linear dispersion, right? You can estimate it. You assume the linear dispersion of Dirac cone and high semi-metal.
Yes.
But your state is a little have a curvature for high energy, right? Yeah, you can expect which value is more reasonable in your model for energy.
Repeat. Means,
You assume this is a linear, but your band is a little far from the, for example,
but actually,
graphing.
I take near Dirac point.
Yeah, I know, but my point is near means you can estimate is graphene has a real band, but you're little far from the K point. This Dirac cone has a little mass.
Yes.
Yes. So that means that this reason is a little beyond your approximation.
Actually, means because low energy Hamiltonian is near Dirac the point. I
know. And my point is based on this your band structure, you can estimate what is the maximum omega or.
Means you want the range of which frequency I have applied.
Yeah.
So I think means
you can estimate which frequency is relevance in your model. For example, in your graph.
I don't remember exact value, but as I remember, because quite long away I have done, it was ultraviolet and infrared region. But that time about that type of frequency. So what happened that if I consider that, okay, this time external applied field is a quantized form. So what happened that the same while semi-metal Hamiltonian I have taken, and then I applied this photon operator like P and P dagger. So it is like creation of photon and annihilation of photons. So above Hamiltonian model is analogous to well-known James Cummings model in optics. So by performing some unitary transform, I can make equivalent to this. So
but wait, the James Cummings Hamiltonian is time independent, right? So that is more like it's the Rabi Hamiltonian which is time dependent, right?
Yes, but if I perform some unitary transform, it can be.
Okay. So that Hamiltonian is still okay. So you still have to do stuff there.
Yes. Actually, means what happened that. Because James Cummings model used for conventional Rabi oscillation, something. Then similar type of things are applied there, and I found that okay, if you perform some unitary transform, you can reach up to James Cummings model, some mathematical. So same thing I have done. So for simplification, I consider that there is only one electron hopping. So there is either no electron, no hole, or one electron, one hole. So I consider this state. So this 0 for no electron, 1 for presence of electron, n is the number of photon. So because
actually this was another point. This equivalence with the James Cummings is because you are considering only one electron, right? Because otherwise you have different statistics and then things. Okay.
Yes. Okay. Actually, what happened? It become very complicated if we tried something. And in case of circular question, I applied, and if I try other. It is not possible to solve theoretically because at that time I used just only Mathematica and it hang. So from that I found I do same thing and then Schrodinger equation and then I found these kind of Bloch equation. So what happened that because there is a distribution of Rabi frequency produce initial dephasing in cis-interval Rabi oscillation is known as collapse. And when revivals refers to resurrection of previously extinguished oscillation due to destructive interference. So the crux of the story I want to say, when I consider external applied field, Floquet oscillation behave like this. But when I consider this external applied field in quantum nature, then this collapse revival spectra has came. So this came because of discreteness of the external light. So I found that this kind of oscillation collapse spectra also exists in Floquet oscillation. So that was my goal. So in summary, I want to say that I studied the phenomena of Floquet oscillation in investigating the inference of that field. It means continuous first and quantized, and then exploring Bloch-Siegert shift in context of Floquet oscillation. Then how we can detect Floquet oscillation inside the pump and probe spectra, and then quantized nature unveiled that collapse revival spectra and Floquet. So these are my selected publication in there, and then that's it.
Questions?
I think Kabia didn't get an answer, so.
Yes.
The first question that I asked, like in Floquet theory, you discussed two energy scales, one from the light and one from the bands. How about the scattering? How do you account for scattering mechanisms in Floquet?
It means that you want to know some Coulomb tricks and that.
Will there be scattering among?
Means I don't just consider one electron, one hole. At that time I don't consider scattering.
Okay, we can discuss this. Yeah.
Okay, more questions?
Question, in the last part, you discussed about the quantum Floquet theory. I missed some points that you need to sense that this is the Floquet theory. I think you introduced and used the quantized field.
Yes.
But did you find some Floquet Hamiltonian?
Yes.
Floquet approach? Yeah.
Yes. Actually, what happened that here I skipped because it was too mathematical. I found it is already become boring. So from here, this Hamiltonian as usual. And in earlier slide, if you remember, I just do Fourier transform method, slow and fast. Here. Because this method here. So same thing I tried there. Like there was making this slow and fast, same type of thing. So because there was continuous field and their photon comes, so discreteness has came and collapse also.
So that then did you also assume that the coupling between the light and the matter is weak?
Weak means what sense? Weak?
The coupling strengths. As far as I know, is the James model. You assume that
There is coupling strength. This. Yes. Lambda. This.
Yeah, lambda.
Yes. Lambda is the coupling strength.
Yeah. So your approach is valid for arbitrary strengths of lambda, or
Actually, means I consider that it's weak, not very strong coupling. But there was a transition. Coupling comes because of electron transition from one to other. So, what sense you want to be? I don't understand.
probably that it is for example, the two electrons transition.
No, one electron. For making models simpler, I just consider one.
Two proton. Yeah.
One electron, because it is, if I consider more electron, it is impossible to tackle by third. One electron, one proton.
in the sense there is the weak copy.
Yes.
More questions? Yeah, please.
And in this part, what kind of experimental setup you are proposing for this quantum?
Actually, because collapsed spectra is well stabilized in conventional Rabi oscillations, it is well stabilized because when we got more powerful laser, we found that there is collapsed spectra in Rabi oscillations. Same type of experiment we can perform in quantum cavity. If you know that quantum cavity, sometime I would say might perform in optics for detecting conventional Rabi collapsed spectra.
Any other questions?
Maybe
Yes, please.
basic question. I just want to understand the experiment. If we don't have time-dependent perturbation, can we just shine the light and measure the transmittance or reflectance, and there the information about the band structure is included?
Yes.
Now, if you have the circularly polarized light on top of that, then how? I just want to understand that what is the role of this probe or pump in there?
Actually, what happened that if you know about a pump probe experiment, so what happened? First, we excite system by pump. Then there is some time delay, and we put probe. But the pump has more intensity, and probe has very less intensity. Otherwise, it will change again some disturbance come inside system. Then there is some dephasing come in pump after applying because system dephasing means return to their original position. So I consider everything, and that's the way. Then finally we consider differential transmission coefficient, because if light pass or some heat pass to the system, then there will be transmission coefficient. So pump with probe and pump without probe, and I got that.
No, but from the pump you already excite the system.
Yes.
And then you want to measure the information of that excitation, like in the time range that it do not decay, or it decay and then measure.
Means
from the pump you excite the system.
Yes.
And then you have the probe.
Yes. So but actually same time pump probe experiment means the same. It is not very large time delay, because pump is for exciting system and then probe for detecting what happens inside system. So it is just big field, but some time delay. You can say some, but it's obvious method. Pump probe experiment is obvious method, but we have taken very stupid.
Usually in those pump probe experiments, you also map as a function of the delay.
Yes.
So it's important to screw the pump and the probe within the delay range.
Yes.
And I didn't see where the delay comes from.
This is this TD. If you see pump plus the time delay in probe, so there is delay. This expression, there is a TD. So this is a time, TD is a time delay between pump and.
Do you think about your wave function is not the Slater determinant of all energy? Only it considers effective single reactor. This is a pyramid system.
Actually, here means I just think that because I have taken low energy Hamiltonian, so it is not one electron like in photon.
But always creation is electron and
hole. So, but
you do not consider the whole state.
I consider that creation of electron on suppose in graphene lattice A, lattice B. So creation on electron on lattice A side and lattice B side, like this. Not one electron or one hole. You can say at one time we consider one, because it's a second quantized form. So one electron, one hole at the moment, because it is not possible theoretically to consider multiple electron or screening. I tried it with Coulomb attraction but not succeed. But see, ask it.
More questions? that's not the case, then let's thank the speaker again. Thank you. And Dr. Kumar will be